Hello, this is Jake Abbott, and in this video I'm going to talk about sets of linear algebraic equations. When we say sets of linear algebraic equations, what we're talking about is this kind of equation. We have some vector y, which is equal to some matrix A times a vector x. And let's say our x vector is an n by 1 thing, and our A matrix is an m by n thing, so our y vector is an m by 1 thing. And so if A and X are both known, then computing Y is totally trivial. It's just matrix vector multiplication, which we covered in the last video. So Y is simply computed. So that's not very interesting to us in this case. The thing that's going to be interesting to us in this video is this case where A and Y are known. And then what we want to know in this case is there a solution for X? And is the solution unique? So this is really what it comes down to. We know this matrix A, we have some Y that we would like to get, and the question is it even possible? Is there some X that we could multiply by A to get Y? And maybe the answer is no. There's no X that I can multiply by A to get Y. And maybe the answer is yeah, but there's a whole set of X's that you could do to get Y. Or you could say there's exactly one X multiplied by A to give you the Y that you want. So this is what we're going to be talking about in this video. The thing is, you got to remember is that what this little equation y equals a times x, it's kind of a compact kind of shorthand notation, right? So it really is a set of equations. So it's m equations with n unknowns. So really, the rows of this, when we look at this, we have y1 through ym, and that's going to be equal to some big A matrix times some x1 through xn, right? And so each of these rows essentially becomes an equation that we're solving. So there are m equations, and these x1 through xn move into these various spots. And so there are n unknowns, and it's the x's, the n unknowns that we're trying to solve for, and we have m equations, which are represented sort of by the rows of the matrix, you can think. So as we look at problems like this, we use terms like the range space, the rank, the null space, the nullity of this matrix A. And that's ultimately these sort of terms, these linear algebraic terms, are what are going to let us mathematically describe the answer to that question, which was, is there a solution for X? Is it unique? And we can sort of answer that question only by looking at this matrix A. So some of the terms that we're going to use is the range space of A. So this is a definition, the range space of A. And what it is it's all the possible linear combination of the columns of A. Because if you think about it, that's what we're talking about here. When we talk about A times X, remember this looks like I can write A as its columns. Column 1, column 2, and we said A was an m by n thing, so we're saying that it has n columns. So all the way to an, times this set of scalars, x1 through xn. So really, when we're looking at this output of this, it's just the linear combination of the columns of A, where I'm multiplying the first column by whatever x1 is and the second column by whatever x2 is. So it's just the output, the y vector of this is just some linear combinations of the columns of A. And so what we call the range space is it's all the possible linear combinations of the columns of A. So what it really means when we say the range space, we really mean what are all of the different y vectors that we could make? Every possible y vector that we could possibly make. If I imagine every single x vector that I have, I multiply every single x vector that exists in all of Rn. So x lives in Rn. Every possible x vector, if I multiply it by a, what are the set of y vectors I'm going to get? Maybe I'll get all possible y vectors in Rm. But maybe I won't. Maybe there's some y vectors I can never make, even though I try every possible x vector. So the range space of A is going to be the set of all possible linear combinations of the columns of A. But that really, when you think about it in terms of linear algebraic equations, means it's all of the possible y's that I could make by multiplying A times all possible x's. So once we have an idea of what the range space is, then we can define the rank of a matrix. And so the rank of A is the dimension of the range space. So in the event, back up here before, if it's possible, if I look at every possible x and I can make every possible y, then I can completely describe this space Rm, an m-dimensional space. And so I can fully describe the rank of this space, this m-dimensional space. So the rank of the A matrix would be m, meaning the dimension of the space that I can span in the range space. But maybe there are some directions in y that I can't achieve. And in that case, the rank of A would be a number that's less than m. But it would be the dimension of the range space. And another way to think about this is the definition of the rank, but it's also the case that the rank is the number of linearly independent columns of A. So if the range space is all of the possible combinations of the columns, then really, who cares if this column AN is already just some linear combination of A1 and A2, then I can't sort of make any new y using AN, because if I could have made it, I could have just made it as a combination of A1 and A2. So it doesn't really matter how many columns there are in A, it only really matters how many linearly independent columns there are in A. So the rank of a matrix is the number of linearly independent columns in A. And that also, the rank, is the dimension of the range space. So all of these definitions just point at each other and reinforce each other. So it's great if you remember all of them, but you can kind of redefine ones with respect to the other. So to kind of summarize this idea of range space and rank, you ask yourself this question: is y, the output vector, in the range space of A? So basically, if you say is y in the range space of A, what you're really asking is, can I make y by multiplying A by some vector x? Is there a vector x that will let me make y by multiplying A times x? If the answer is yes, then you say there is a solution. So there is a solution for x, and and it's actually maybe more than one. And then if the answer is no, then there is no solution. So let's try and, this might seem like I'm talking in circles, but I've sort of separated two things out. We were originally looking at this set of equations, y equals ax. We're trying, you give me a y, and I'm trying to figure out if there's an x that I can find that if I multiplied that x by a, I would get y. But to solve that question of whether X exists, if that solution exists, I only look at the matrix A itself and I say, is Y in the range space of A? So basically, can I make Y by the columns of A? So it's like you've looked at this problem sort of from a different angle. And this is how range space and rank relate to each other. So I'm also interested in vectors of X that when I multiply by A, I get the 0 vector. So if I take a vector A times X, and when I compute that, I get 0. I get the 0 vector. Then X is a null vector of A. This is a definition, a null vector. So what is a null vector? It's a vector that I multiply by A and it gives me the 0 vector. Okay, so it's totally obvious and totally trivial that the 0 vector itself is a null vector, right? And it's so trivial that it's just completely uninteresting. So we don't even really count it. Of course, if I multiply A by X, I'll get 0. If X is 0, if I multiply A by 0, I get 0. That's always going to be true. So it's so kind of silly and trivial that we don't really count it. And then when we really talk about the null space of A, okay, the null space of A is the set of A's null vectors. And then we say the nullity, this is also a definition, is the dimension of the null space. But because this X equals 0 is so trivial, we don't count it when we're thinking about the nullity. So if the only vector that makes this true is the 0 vector, then we say the nullity is 0. We don't say it's 1. For the nullity to be 1, there actually needs to be a direction in this X space that's not 0, that when I multiply it by A would give me 0. So then we have this other definition that says that the number of columns of A is equal to the rank of A plus the nullity of A. So I take the rank, I take the nullity, they always add up to the total number of columns. So if I take a matrix that has 5 columns and it has only 3 linearly independent columns, then that means I have a rank of 3 and a nullity of 2. And so if I can solve for either the rank or the nullity, I can immediately know what the other one is because they have to add up to the columns of A. And so it would be reasonable to say, well, are the number of rows of A also equal to the rank and the nullity? And the answer in general is no, they're not the same. And the reason why they're not the same is because in some ways the columns of a matrix are more important than the rows. I mean, let's go back to our basic equation that A times X is equal to Y. And we said that Y is nothing more than some linear combination of the columns of A, where X is the weighting function of how much do I weight each of the columns of A. So it's really the columns of A that are really kind of important in thinking about the solution of Y. So it's the number of columns of A that add up to the rank plus the nullity. Don't confuse that. Now, in the event that A is a square matrix, then this is also the number of rows. But it's a total coincidence that that's true. I mean, really, if A is square, it's still the number of columns that equal this, But since the number of columns and number of rows in A are identical to each other, then you could replace this with the number of rows in the case of a square matrix, but only a square matrix. But this statement about the number of columns of A equaling the rank plus the nullity is always true, even if A is a non-square matrix. So one thing that is true, though, this equation is only true specifically, or this equation is always true. Replacing this columns with rows would be true for a square matrix, but even for rectangular matrices, we can say that the rank of A, which we previously said is equal to number of linearly independent columns. We previously said that. Well, it's also true that the rank of A is equal to the number of linearly independent rows. And this is always true, even for non-square matrices. So if A is an m by n matrix, so m rows and n columns, then the rank of A is less than or equal to the minimum of m and n. So let's say I have a matrix that's 3 by 5. Then I don't know what the rank of A is, but I know it's at most 3, because the minimum of 3 and 5 is 3, and my rank of A is less than or equal to 3. So, and it's not saying the rank is equal to 3, it's less than or equal to 3. So I take the number of rows and the number of columns, and my rank is never more than the minimum of those two things. And if you think that the rank of A is the number of linearly dependent rows and the number of linearly independent columns, then you could never max out more than whatever is the least. So if I have 3 rows and 3 columns, how could I ever have a rank of 4? Because that would mean I have the number of linearly independent rows is 4, but I only have 3 rows, so it doesn't make any sense. So this sort of makes sense when you think that these two things are always true. There's another interesting thing about rank that we should keep in mind. So if A has rank m and B has rank n, so I have two matrices, A and matrix B, and this has rank m and this has rank n, and I'm looking at this multiplication. C is equal to A times B. Okay, so I'm making a new matrix. Then here's some things we can hang our hat on. The rank of this matrix C is always less than or equal to the minimum of m and n. So basically, if I take a rank 2 matrix and I multiply it by a rank 5 matrix, the matrix I get out is either going to be rank 2 or even less than rank 2. So basically, you can never go up in rank by multiplying matrices. You can only maybe go down, but you can never go up. So it's sort of like once you have a certain minimal amount of information, you can't get more. You can only sort of subtract from it. And this is going to be another tool that we're going to make use of on occasion. So let's sort of kind of ground this home with an example. So let's say we have this matrix A, and this matrix A looks like 1, 0, 0, 1, 1, 0. So it's a 3 by 2 matrix, and how many linearly independent columns does it have? Well, it only has 2 columns to begin with, so the question is, are they both linearly independent from each other? So can I make this right column by multiplying the left column by some constant? No, I can't. There's no scalar I could multiply this by and get this. Because of this 1 here, I could multiply this by 5, but 5 times 0 is 0, and no matter what scalar I put there. So it's got 2 linearly independent columns, right? Now, so that means that the rank of A is equal to 2. Now, we shouldn't be surprised when we look at the number of linearly independent rows that we also get 2. It has to be 2 because the rank of A is defined as both. So when I look at the linearly independent rows, I see I've got this row here, I've got this row here, and there's no way to make one a linear combination of the other. And then I've got this row, but this row is not linearly independent because it's very easy for me to make this row by some linear combination of these rows. I'll give you an example. All I have to do is go 0 times the vector 0, 1, and I get the row vector 0, 0. So it's very easy for me to multiply some scalar times one of the rows and get the third row. So the third row is not linearly independent, and so I have 2 linearly independent rows. That was not a surprise to me. I knew that had to be the case. And if you ever get it so that you have a different number of linearly independent rows from linearly independent columns, then you've made some mistake. And so this is the rank of A. So the rank of A is also the dimension of the range space. So I should be able to find, if I'm looking at this y equals A times x, where A in this case is a 3 by 2 thing, x is a 2 by 1 thing, and y is a 3 by 1 thing, I know that the range space has dimension 2. But y is an R3 number. So I can't form every possible y in R3 because my range space is only dimension 2. And it's pretty easy to see what types of y's I can't form. I mean, if y is equal to this 1, 1, 0, 1, 0, 0 times any x1, x2, then you can figure out that y is going to equal x1 plus x2 in this entry. It's going to be equal to x2 in this entry and 0 here. So I can never form a y vector that doesn't have a 0 here. So I can only span a 2-dimensional space within R3. And in this case, it's pretty easy to visualize that 2-dimensional space. So if I sort of think of this as entry 1, this is entry 2, and this is entry 3, I can form any vector in this plane that's described by 1 and 2. I can form that vector, that vector, that vector, that vector. That's anywhere in this sort of horizontal plane here. But I can never go vertical. I can never move up in the third direction because this will always be 0. So even though y is an R3 space, it's a 3-dimensional vector, my range space is only a 2-dimensional subspace of that space. So this is how we interpret the dimension of the range space relative to R3, and it's pretty obvious that the range space at its maximum could only be as big as the dimension. So the highest my range space could possibly be is 3. That would mean I can form any vector in R3. In this case, my dimension of my range space, which is my rank, it was only equal to 2.